Okay, so now that we have covered line inductance, so let's look at line capacitance. For line capacitance, the concept of calculation is very similar to line inductance. But in this case, for line inductance just now, we looked at the magnetic field, so it relates to current. For line capacitance, in this case, it relates to electric field, so therefore it relates to voltages. Now, for line capacitance, the basic equation is C equals to Q over V, where Q is charge, V is actually the voltages. So, let's look at this conductor shown in figure 4.14, whereby in this particular figure, we assume that the conductor has a radius r carrying a charge of q coulombs per meter length as shown. We assume that the flux is radially around the conductor. We also assume that it is equal, the total electric flux is equal to the charge of the conductor. And just now we looked at B, which is magnetic field density, or magnetic field intensity H. Now in this case, now we look at electric field intensity, which is E. So from Gauss's law, the magnetic field density is Q over A, as shown here. And if we were to expand, because this is a cylinder, so it's Q over 2 pi x, which is the cross-sectional area. So if we look at electric field density E, so E is equals to D over epsilon naught, where epsilon naught is permittivity of free space, which is 8.85 times 10 to the minus 12 farad per meter. So based upon equation 4.6 and 4.61, then we create equation 4.62, which is E equals to Q over 2 pi epsilon naught x. Okay, so if you look at the particular position between D1 and D2, similar to the external L. So in this case, V12, which is between position D1 and D2, we integrate that for E. So what we get at the end is Q over 2 pi epsilon naught ln D2 over D1. So now let's expand it further. Let's say that we have two conductors with the radius r and charge value of Q1 and also Q2. So let's look at the effect on capacitance, okay, where we assume that the distance d is much bigger than the radius r, okay, and the height of the conductor is larger than d, which means we assume that there's no earth effect to this. So therefore the charge is uniformly distributed. So the potential difference for this now would be shown in equation 4.66, whereby we look at its impact between 1 and 2 for Q1 and also the impact from the Q2 point of view. So we have this one here that represents Q1, this one here represents Q2. Now, since from there, we assume that Q2 is equals to negative Q1 because we assume that the conductor is identical and the voltages is identical. So now it reduces to just equation 4.67. So based upon that, we apply back to the earlier equation, which is C equals to Q over V. Therefore, we have equation 4.68. Now this is the basis of the capacitance equation, where we shall expand it further so that we can actually apply it to a particular conductor configuration. But the form that you see here is very similar for the next set of capacitance formulas. Okay, so equation 4.68 here refers to the line-to-line capacitance between the conductors. So usually we define it as shown in figure 4.16, where we refer to capacitance to a neutral point. Okay, so when we refer to capacitance to a neutral point, so we call it, the equation now simplifies to equation 4.69, which is 2 pi epsilon naught over ln d over r farads per meter. So taking into account epsilon naught is 8.85 times 10 to the minus 12, it simplifies, and also assuming that we want to look at microfarads per kilometer, then it simplifies into this form here. Okay, so the top part is fixed at a value of 0.0556. So now we need to expand the bottom part, ln d over r. How do we expand it further so that we can do more calculations for C depending on conductor design? So let's look at multi-conductor configuration. Okay, so let's assume that in here I have 6 conductors, each carrying its own charge Q1, Q2, Q3, Qn. Okay, so assuming there's no distortion in the charge, we assume that the total Q contribution is cancelled. It will cancel off each other, which is equals to 0 here. Okay, so based upon that, we try to calculate the potential difference between the conductors. We'll get equation 4.72. Okay, so let's look at capacitance of three-phase lines where the distances are different and it is transposed. So what we'll do is, since we assume that it is balanced, so QA plus QB plus QC equals to 0, and assuming there's no effect of ground and shield wires and the lines are transposed, so therefore C now equals to 2 pi epsilon naught over ln GMD over R, which is farads per meter. Or in terms of microfarad per kilometer, now it becomes equation 4.86. So notice that now we have introduced the concept of GMD, which is the same thing, geometric mean distance. And GMD, if you notice, is similar to how we calculate the GMD for L, because it refers to the physical distances between the neighboring conductors. Okay, so the capacitance per phase is found to be as shown. Okay, so the bottom part here, which is RB, is actually similar to DS, but in this case it is called GMRC. Just now, the R prime value, which is also called DS, is known as the GMRL. So for capacitance, when we have bundling, for 2 subconductor, it will be equation 4.88. For 3 subconductor, which is equal to equation 4.89. And for 4 subconductor bundle, it is equal to equation 4.9. Again, you must remember this formula because you may have a bundled configuration in your exam. So when you have bundle, the GMR value will be different. Okay, so let's apply to the same problem as earlier, where we have a double circuit line, same configuration as shown before, which is figure 4.13. So let's look at how it impacts the capacitance. So the basic formula is still the same, which is ln GMD over GMR. Okay, or to be exact, sorry, the capacitance formula is 2 pi epsilon naught over ln GMD over GMRC. which is either equation 4.91 or equation 4.92, depending on what you want to calculate. So the GMD should follow the same set of formula. Okay, should be still the same as shown here, no different. The GMRC will follow the same grouping, but in this case RB will depend on the bundling that you have. Okay, as mentioned here. And the total GMRC is very similar to the previous, where we actually combine everything together.